Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so our second speaker is Trevor Darrell. He's a professor of computer science division at UC Berkeley. He and his group has done many influential work in, especially in deep learning for computer vision. So recently, his group developed region-based CNN, which is a state-of-the-art framework for object detection. And also, his group is well known for developing Caffe, which is a widely used open source library for deep learning. So today he's going to talk about adaptive, articulate, and actionable deep learning.
Thank you very much. So I'm very excited about the performance and success of deep learning, and in computer vision, especially not just its absolute performance on fully supervised tasks, but its flexibility and ability to work on a number of related problems, and also to work across modalities. And so that's the focus of what I'll talk about today, summarizing some of the work going on in my group and in collaboration with others at Berkeley, how these visual models not only can adapt across visual tasks, but to language, and then ultimately to robotics. And so that gives me the title, Adaptive, Articulate, and Actionable Deep Learning. I'll mention some of our recent work on deep learning that can adapt to new domains, especially non-IID settings. I'll spend a considerable amount of time on this models that can jointly learn visual representations and natural language descriptions, focusing on what's very recently exciting, making these models compositional and able to individuate objects in a scene, not just tell a story about the entire scene, but talk about or individuate objects within a scene. And then finally, I may actually defer to my colleague Peter Abil, who's speaking later in the session about our joint work, which also takes these models, modifies them in some important ways, and directly uses them to learn action policies from visual inputs. So first, a few words about domain adaptation. We want to train in one environment. Maybe we learn images from the web, test in another environment. Maybe the classic example is we have a robot going around in an environment. And even the best deep learned algorithms, deep learned representations are far more invariant to domain shift than any prior visual representation that we used. But indeed, even deep learned representations still suffer if the training data doesn't match the testing data. And there are some very simple and efficient things that you can do to improve performance, to adapt deep learned models to new domains. And of course, it goes without saying that the simplest thing that you could always do is fine-tune your models. And so if you have lots and lots of labeled training data in your target domain, we don't even need to put up any slides on this. You can just go ahead and fine-tune. So we're interested in domain adaptation when you have few or no labels in your training data, maybe one or two per category. How can you adapt a deep model with such little training data? And indeed, one of the main underlying concepts we explore is this idea of minimizing discrepancy across domains. And this is informally related to the classic idea of dataset bias that Alyosha Efros and Antonio Torralba introduced several years ago when they had this paper that some of you may remember from the vision community, the Name the Dataset game. If you can guess what dataset your samples are coming from, you probably have a problem, and their paper articulated why. And so that is one good idea one can employ. Let's have visual representations that are invariant to the domain shift that we want to not suffer from. Let's minimize discrepancy. So in our most recent work, we explicitly optimize for this in a deep architecture. We train deep domain classifiers and penalize them for actually being able to tell the difference between domain labels. We can show that this learns representations, that actually brings samples of the same class across domains closer together, and then finally classifiers that were trained in the source domain work well. You can do all of this without any labels in the target domain, any class labels. So I probably don't have time to go into detail in this architecture, but it's essentially two paths, one for each domain, where in addition to the standard classification loss over here, I don't think you can see, yeah, okay. Over here we also have these additional losses for domain confusion. And we can visualize the network actually learning representations that can't tell the difference between domains. The second twist here is if you have a few labels, how can you make the most use of them? Well, you can obviously fine-tune, but you can do something slightly better than that, which essentially amounts to taking the idea of the dark knowledge concept from Jeff Hinton a few years ago, which he applied to simplifying networks, and I guess you can think of that as or generalize that to this idea of domain adaptation, because you can train more efficiently with the soft labels, with the labels that you have, if you take advantage of intercategory correlations in the source domain and apply them in the target domain. So you can see what activations you have in the source domain across categories, not just taking the single hard label loss, but training the target domain with a soft label loss as well. And both of these, our final architecture integrates both of these ideas for domain adaptation, task correlation transfer through these soft labels and domain confusion. And both of them help and really outperform just collecting the data together into an initial training set. And as I said, many times you have no labeled data in your target domain and need to make use of it. So this is the paper at ICCV and is on arXiv, and if you'd like to read more, I'll refer you there. So now I'd like to talk about the second major bullet, articulate. How do we have representations that not only can recognize images and do so across domains, but actually tell a story about what's happening, map directly from images to words. And I'm sure everyone in this room, or nearly everyone in this room, has seen the great plethora of models and advances that happened over the past year of architectures of forms similar that you see on this slide, where you have a visual CNN processing an image and being input to a language model, perhaps a recurrent language model based on an LSTM that could then generate sentences or captions related to images. And I won't say more about those models than that because they've gotten so much attention over the last year. And we had one of them, and many other folks in the room had others. And actually, nearly all of them, or I would say all of them, had the following problem. Maybe not all of them, but certainly ours had the following problem, which is they really were limited to their training data. And they weren't compositional in important ways. And one way they weren't compositional is they could only talk about things they'd seen in previous caption data. These models were trained on paired corpora of images and captions, and they learned to generate captions that were appropriate when they were within the space of their training data, as you would expect. But that led to unfortunate performance when you, for example, have this picture of something here swimming in the water, and it's really not a dog sitting in a boat in the water, which is what our system, or many systems that were trained on the available corpora at the time, would have output. But we have lots of other sources of knowledge, lots of other sources of visual data. We know that that's not a dog because we've seen lots of dogs on ImageNet, and that doesn't look like a dog. And there's actually lots of unpaired text data as well that tells us a lot about language models that go beyond the language models that are baked into the paired corpora. So the first compositional captioning model I'm going to put forward is what we call the deep compositional captioner, and it really takes advantage of lexical generalization, taking advantage of other data that we have, unpaired data, either image tag data or just text data, and indeed it can learn to take this image and speak about the otter that's sitting in the water, even though it's never seen a caption involving an otter before. And we do that by extending the previous model to have structure to allow it to be separately trained across different data sets and integrated in interesting ways. And one of the key ideas, at least in our current work, is for each new term we want to bring into the captioning model, for example, from ImageNet, we have to find a proxy word in a language model, in the paired corpora, perhaps, to say, how should I speak about otters? For example, you might find that you speak about otters the way you do about dolphins, or you might speak about zebras the way you speak about horses. And once you've integrated a zebra, actually I think zebra is in MS Coco, but for a word that's not in MS Coco, once you've integrated it in, for example, I think the next slide has that. I don't think there's a toad in the typical corpora that people train on. So the typical models wouldn't be able to caption this as a toad. But knowing that toads are sort of like birds, and that can be automatically discovered from the models, our model is able to caption that appropriately. We also have this results on video captioning with a similar idea. And if you'd like to learn more about this, we have an archive that you can read by Hendricks et al. Okay, so the second major idea about captioning in these language models I'd like to put forward is more traditional linguistic compositionality. Especially when you look at visual question answering, there's been a lot of, I think, very exciting models on how attention can be used for visual question answering, but I think we really need compositional competence to make a serious dent in visual question answering. Maybe not for the data sets that we have today, but I think to convince anyone that we really know what we're talking about when we answer questions. And by compositionality, we mean the ability to separate out different processing structures. For example, finding the stuff that are attributes versus finding certain nouns, and then doing operations such as counting on them. So we have recently, this is joint work with Dan Klein at UC Berkeley. We've recently destroyed my laser pointer, but that's probably fine. We've recently proposed an architecture called neural module networks, which composes a new neural graph corresponding to a sentence. In the current version of the work, it's actually using a traditional NLP parser, but that can obviously be replaced with a deep architecture, although the traditional architectures work exceedingly well for the class of questions that are actually in these data sets. And comprises a new deep architecture for each sentence that it sees and trains them jointly. For example, if you wanted to have a sentence, what color is his tie, it would create a small little visual routine to find the tie, extract the color, and answer the question. In the interest of time, I'm going to skip through a few of these slides and point out that what's really powerful about this is when you want to have very complicated logical queries. Is there a red shape above a circle? That's something that many of the existing networks have trouble with, but this approach does. And currently, an architecture based on this approach does very well on toy problems that are more or less impossible for many existing architectures to solve. But it's able to ask complicated queries about, how many square green things are there in this image, and that would be harder for the traditional approaches, or at least many of the traditional approaches that have been reported. And this architecture also does well on the traditional VQA data set that we see in a wonderful poster over here, although it's not clear that there's enough complexity in those questions yet. So I think that's a topic of future work. And again, there's an archive on this if you'd like to see it. In the 1 minute I have left, or hopefully 2 minutes I have left, I'd like to talk about another extension of this, of the integrated vision and captioning work that I think is particularly exciting for robotics, or for any setting where you'd like to talk about things in the world to an agent. We call it natural language object retrieval, but it's really this idea of referring to things in scenes. And we have recently proposed a model that not only can talk about an entire image, but actually can figure out which region in a scene is the region that somebody's trying to refer to. So if I want to speak about something to a robot or an agent, I'd like to use natural language and say the guy with the blue shirt, or the guy to the left of the guy with the blue shirt holding a pole, and I'd like the robot to know, or the system to know, which person I'm talking about. So that's what I've just said. So we have a new architecture that generalizes the existing vision language models to include object, spatial context, position within an image, and is able to take image regions and score strings that are presented to refer to a scene. And there's a very comprehensive data set that Tamara Berg collected called the Refer It game data set, which has actually been out there for several years and hadn't really gotten much attention. We show results on that I think are fairly exciting. There's the white hat can be found in this image. The leaves on the left tree can be found, and so on and so forth. So we have an archive on that. I think there's also some interesting related work from Google. Kevin Murphy has a similar model, and also I guess a great new data set also on the way, and we look forward to that. So I have negative time, and so for my last thing, I can just give it to Peter Beals to talk about it later in the day, how we have joint models that map from pixels to action. And I've summarized these three topics that are really exciting to show how deep learning is bringing different fields of AI together, kind of core machine learning for domain adaptation, vision, language, and robotics. And these are the archives that I mentioned today. And I'd like to thank all of my co-authors explicitly for all of the work that they did on these projects. Thank you.
So we have time for a few questions. So can you please come forward if you have any questions? So I have one question. So how far are we from doing some more deeper level of question answering, such as understanding the intention or intent or some why, or understanding what's going on with the image?
I think you just have to read these archives and you'll learn all about it. Okay. Yeah, deeper. It's a hard question because I have to know what you mean by semantics and deeper. I mean, you mean the way people...
So why a person...
You mean the way people do it? You mean like a system that can behave the way a person behaves when it answers a question, in the sense that it can explain what it's doing? So I think that's a very exciting area of future research of how we can have these explainable architectures. And I think there's reason to believe that these deep models can be trained to do that.
Okay, thank you. Yes.
Hey, Trevor. So for the example where you were dynamically constructing networks, can you give a flavor of what kind of methods you're using to instantiate the network? Are these
that's
traditional
just
NLP methods?
It's a standard Stanford parser, I guess. I'd have to defer to my... it was really Jacob Andreas, who's Dan Klein's student, working on that, but it's a traditional approach to the parsing step. And once you've parsed the phrase, the semantic interpretation is done with deep architectures that are jointly trained across all sentences. So the grounding of the term red is common to all of the modules that involve the word red.
Okay, any other questions? Okay, yes.
So Trevor, I can imagine 50 archive papers describing great work in a variety of areas, but System 3 doesn't do what System 27 does. And how are we going to integrate all these capabilities into a single larger system?
That's System 98.
Okay, so but how?
It's all in cafe, I guess. I'm not sure. Well, I do think that as I started the talk, I do believe that it's far more likely, or it seems there's much more promise for that in these architectures or in the deep learning framework than in traditional. I mean, language and vision people have been talking about joint grounding for ages, and very little happened that really looked exciting to people outside of that community until these deep architectures, we could just start gluing them together. And maybe now we're going to start gluing them in slightly non-trivial ways that aren't just undifferentiated goo, but have structure inside of them. But it'll probably still be a long way until we have broad universal AI competence, but I'm more excited than I used to be about that topic.
Okay, so thanks Trevor again.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.